Looking at the schedule here, May 16th, so we have a final exam coming up in 3 weeks. The final exam, I'm going to divide it into two parts. The first part of the final is going to be multiple choice. That will be 3 hours during lab. This is lab day on Wednesday. Then the second part of the final will be like drawings, Lewis structures, or nomenclature, or chemical reactions, that type of stuff that doesn't lend itself well to multiple choice. And so it could be drawing the hybrid orbitals, this kind of stuff. And so that's coming up pretty soon. We're going to be finishing up chapters 10 and 11 here this week. All right. So what we're going to do is I'm going to go back, since I've been jumping around quite a lot of the chapters. Let's go back to chapter 10. We're going to look at Lewis theory, covalent bonds, polar covalent bonds, ionic bonds, electronegativities. So let's take a look at bonds. Here, what types of bonds do we have? As far as bonding goes, we'll start off with metallic bonds. You know, what holds the metal atoms together. And for metallic bonds, we have delocalized bonding electrons. The bonding electrons are the valence electrons. The core electrons are what we call localized. Localized means they're in the 1s, 2s, whatever orbitals there are. But delocalized means that when we look at the valence electrons are free to move. You know, this is what gives metals their electrical conductivity. And so essentially the electron is free to move throughout the entire metal structure. However, the nuclei and the core electrons are fixed in position. And so they call this the electron C model. It's the electron C model because the electrons are free to move like ocean water. And the nuclei and the core electrons are like pure pilings, which are fixed in position. Now, what holds the nuclei together is this negative charge around here. The nuclei are going to be attracted to the negative charge region. Another interesting aspect of the electron C model is the electron isn't confined to the atom. You know, if the electron were confined to a single atom, then we call that electron in a small box, because the wavelength of the electron is comparable to the size of the atom. However, when an electron is in a metal like this, a metallic solid, then it's in a very large box, where the wavelength of the electron is negligible compared to the size of this. And so this is what gives the behavior of like tungsten filaments. Tungsten filaments are a continuum of allowed energies, basically because electrons in tungsten are pretty mobile. They're free electrons, essentially. They're still confined to metal, but they're so much room, and you consider those effectively free. And so, an electron in the big box. But anyway, this gives Interesting other interesting properties. So metals are like black body emitters, versus if we're looking at an atom, it wouldn't be a black body emitter. It would have a quantized line spectrum. Another interesting property of this is it has non-localized, non-directional bonding. That is, if I move, let's say I move these atoms a little bit, like 5 degrees down relative to these others, is that really going to break the bond? No, this doesn't have really directional bonds. In fact, if we look at a gold in the solid state, we'll have an atom here. And so this gold atom is going to be bonded to other gold atoms. And in fact, we can fit 6 gold atoms in the same plane here. And so it's going to be bonded to 6 gold atoms there, and then we can fit an additional 3 gold atoms on top. So this would be the 3 gold atoms on top, and then an additional 3 gold atoms on the bottom. And so each gold atom is bonded to 12, 6 in the plane plus 3 on the top plus 3 on the bottom, 12 other gold atoms. And the bonding is not really directional here. It's fairly non-directional. So if I displace it, let's say I move the gold atoms a little bit, they're still in contact. So in other words, metals are malleable, which means I can deform them or shape them like clay into different shapes. Metals are also ductile. Ductile means I can draw them into wire. And so we can see that a little bit in this electron seed model. Okay. So if I have gold, what's the hybridization of that? If there's 12, what's the shape and the geometry and the hybridization? Well, we don't do that. We have to use the other theory. We have 2 kind of theories, and they're complementary. One is the rigorous, the other is the light version of quantum mechanics. And what do we call those 2 different bonding theories?
There's one valence bond theory.
Valence bond theory. Valence bond theory is where you take the atomic orbitals, whether they're unhybridized or hybridized, and overlap them. What's the other one? A molecular orbital. Molecular orbital theory is the rigorous approach to bonding. And so the electron seed model we can describe in terms of MO theory, molecular orbital theory. This works best. And it turns out, when we look at the MO theory of this metal here, we have what are called bands of molecular orbitals that are closely spaced in energy, like a continuous band of molecular orbitals. And this is shortened to band theory. Band theory of solids. And so when we apply molecular orbital to solids, we end up with band theory, which consists of bands of molecular orbitals. And we get things like conduction band, valence band, that type of stuff, which is discussed in Chem 1B. We'll talk more about molecular orbital theory in chapter 11. So those are metallic bonds. Metallic bonds range in strength. Metallic bonds can be very strong or quite weak. And you can get an idea of how strong the bonds are, depending on the melting point. How hard is it to melt, and break the bond? So bond strength or bond energy we see a wide variation. from very weak, like mercury. You know, mercury is a liquid at room temperature, but mercury is a weird one. It's an unusual case. But what metals have weak bonds? Do you know which metals kind of have weak bonds? The alkali metals. The alkali metals have weak bonds. You can cut a lot of alkali metals with a butter knife. Even a plastic knife would probably work on alkali metals. And their melting points are fairly low. Like the melting point of sodium metal, do you know what it is? It's less than 100 degrees C. Less than the boiling point of water, sodium melts. Cesium melts a little bit above room temperature. But then there are metals that have extremely high melting points. Like tungsten has a very high melting point. That's why they use tungsten in filaments. They use tungsten in light bulbs, the old-fashioned light bulbs, because you can get it very hot. When you get it very hot, then it starts to emit radiation, black body radiation. Well, the problem with tungsten is it's easy to oxidize. And therefore, you have to prevent it from oxidation by encapsulating it in inert gas. Inert gas would be like maybe nitrogen, but you have to watch out because nitrogen can oxidize things as well and form nitrides. You know, but it's better than oxygen, which is a much stronger oxidizer. Or you can use argon, which would be better, or helium. Helium is tough because it's hard to contain those small atoms. Those tiny atoms can diffuse through a lot of barriers. What would be better than tungsten? That has a high melting point but isn't as reactive. Tungsten's W. Like platinum would be very good. Platinum has a very high melting point and it is very hard to oxidize. It's got strong bonds. Gold, too, but those are too expensive to use in light bulbs. But if you could, those would make excellent light bulbs. And so we see a wide variation in bond strength related to so typically we think of in terms of melting points for metals. In addition to metallic bonds, we have covalent. And there's two broad categories of covalent bonds. What are they? Yeah. We'll start off non-polar and polar. And then we have the most polar. The most polar bonds are called ionic. So nonpolar is usually characterized by delta En, difference in electronegativity of from 0 to about 0.5. Polar bonds, let's go from 0.6 to 1.9 or something. Ionic bonds, we'll just go above 2. These are rough. There are some ionic bonds that have delta Ens less than 2. And so there are multiple factors, not just delta En, that dictates. And in fact, there's a range. You know, there's a continuous range of bonds. And a continuous range of bonds can be represented in terms of percent ionic character or percent covalent. And so something that's totally nonpolar has 0 ionic character, 100% covalent character. Something that's ionic has like 0% covalent, 100% ionic. But something that's polar covalent will have some percentage of ionic character in there, but not enough to call the bond ionic. And so this is just differing degrees of polarity. Polarity is this distortion of the electron cloud. LTEM. And so we can take a look at the electronegativities. Do you guys remember the most electronegative element on the periodic table? Fluorine. Fluorine gets a 4.0. This is from Europe, so common, so point, decimal point, period, whatever. Aren't the most precise. If you look at it here, they have it listed as 398. And we'll just round it to 4.0. We don't have to be that precise. Electronegativities are there are other factors that go into the electronegativities, and so they aren't used so precisely. And if you need a more precise, more accurate electronegativity, there's other electronegativity tables out there. These are called the Pauling's electronegativity. But there are other electronegativity scales that are named after other famous scientists. And those are a little bit more accurate because they take into account other factors like how many bonds are to the element, etc. What we're going to do is we're just going to stick with Pauling's, which is simple, but maybe all. Okay, so let's go back over here. Take a look at some examples. Chlorine is very electronegative. Chlorine has a 3.0 on the electronegativity scale. But if it's in a tug of war with another chlorine, which is also 3.0, both are highly electronegative, but when we look at the difference in electronegativity, what is it? It's 0. What's the hybridization on chlorine here? If you were to hybridize it, what would you hybridize it as? SP. What? Okay. SP1. Okay. Anybody else?
SP3.
SP3. Yeah, you don't go off the number of bonds. Go off the number of groups of electrons. We have 3 lone pairs plus 1 bond. So it's 4 groups. 4 groups is going to require 4 orbitals. 4 orbitals would be SP3. Yeah. It's going to be SP3 because we're going to try to maximize the separation between the lone pairs. And the maximum saturation would be 109-degree angles between the lone pairs, although we can't pinpoint the lone pairs. We'll try to say the general proximity of that. And so we got an sp3 orbital here overlapping with the sp3 orbital here. There's an even tug of war. And so what creates the bond, what holds the bond together, is this. What holds the bond together is this increase in electron cloud, increase in electron probability in the internuclear region. internuclear region is between this nucleus and this nucleus. That's called the internuclear region. In the internuclear region, we have two regions. We have one that's directly in the internuclear axis. So the internuclear axis would be the line that connects the two nuclei. So if we look at the internuclear axis, we have overlap within the internuclear axis. If we have overlap within the internuclear axis, we call it a sigma type bond or a sigma bond. And so this would be an sp3 hyphen sp3 sigma bond. Sigma indicating the overlap is within the internuclear axis. If the overlap is outside the internuclear axis, we call it a pi bond, like the Greek letter pi. The thing is, this is nonpolar because it's an even pole, and therefore we expect this electron cloud in the bonding region to be very symmetric. We have three color coding schemes. The three basic colors are red, blue, and green. And then we kind of mixture of more red, more blue, with other variations. But this would be represented as green, right? This would be represented as green because it's not polarized. Polarized means that there's a distortion in the electron cloud, and there's no distortion in this electron cloud. How strong is this bond? Let's take a look at how strong that bond is. Okay, here for metals, we like to look at the melting points, let's say. We could also look at the bond energies, but for this, we like to look, especially covalent bonds, we like to look at the bond energies. And so let's take a look at how strong that bond is. The chlorine-chlorine bond is 243 kilojoules per mole to break. Now, what does that place that in roughly? Let's take a look at the range of the bond energies. The bond energies vary from weak to strong. What's the weakest bond you can find on the chart? Yeah, the oxygen. The oxygen-oxygen single bond is very weak. This is called a peroxide bond. And so we try to avoid those. If you're writing Lewis structures, you try to avoid oxygen-oxygen single bonds because those are so weak. They're so weak that visible light will break them. And so peroxides are unstable. Also, what else is unstable here? The next weakest bond would be iodine. So iodine's got to be protected from visible light because 151 kilojoules, visible light can break it. So those are weak bonds. The strongest bond is what? Yeah, nitrogen-nitrogen triple bond. 946 kilojoules, we'll just call it 1,000. So bond energies vary from about 100 to 1,000 kilojoules. And so the chlorine-chlorine bond's at 243, which is on the weaker end of the bond spectrum. That's because these sp3 orbitals are kind of big. Why are they kind of big? Because they're 3s. They're hybridization of 3s and 3p, which are already big orbitals. And so it makes it a bit weaker. Is it 3? Yeah, chlorine. Okay, let's go on. But it's still really good. For single bonds, the average is around 400, let's say, roughly. For double bonds, it's higher, and triple bonds are the strongest. Triple bonds are going to be the strongest and the shortest because I'll talk about the double bond in a little bit. Because there's more electron density in the internuclear region. All right, let's take a look at something that's less evenly matched. So this is what we call nonpolar covalent. And then we go to HCl. What's the hybridization on chlorine? sp3. And then hydrogen has no hybridization. Hydrogen is going to be an s orbital, like this. And since the overlap region is in the internuclear axis region, we'll call it an S-sp3 sigma bond. HCl. So how strong is an HCl bond? 431 kilojoules per mole. That's pretty strong. Visible light's not going to break this. Break it. Shouldn't break it. Only ultraviolet will break it. But the electron cloud here is polarized, meaning it's distorted. And the reason is because chlorine has a stronger pole. If we look at the electronegativity, it's not evenly matched like over there. Hydrogen's weaker. Since hydrogen's weaker, it's going to have a harder time keeping the electron cloud or keeping the electron centered around it. And so the electron's going to spend more time around chlorine. The delta En here is 0.9. 0.9 puts it in the polar covalent region. And we say that this bond is polar. There are different ways to show it. One way is like this, where the electron cloud has been distorted. Another way of showing this is by using electrostatic potential map. The electrostatic potential map has this color coding system. So for HCl, what color are we going to expect? So if we're going to map this out, do you know what the color coding is? Green is neutral, like there's no charge. Well, let's figure this out. When we do dipoles like this, when it's polarized, we see one end becomes more negative. Since chlorine has more electron cloud around it, we give it a delta minus. Indicating a partial negative charge. And then hydrogen would get a delta plus. delta minus, delta plus. Another way of doing this is by writing a dipole. The dipole is going to be an arrow pointing to the negative end with a positive tail. So that's showing the polarization here. And so these are three ways to show it. Another way of showing it is via the electrostatic potential map. Here. Red regions would be regions of high electron density or low electron density. And blue regions would be regions of low. And green is just regions break even. And so the other way of representing it is the hydrogen would be blue and the chlorine would be red. That's in the electrostatic potential map. The electrostatic potential map comes about because we try to map out the electron cloud. We map it out by looking at all the orbitals and filling those with electrons and then seeing how that is in space around that. So we can see it here. This is the electrostatic potential map of HCl. The hydrogen is blue. Blue is a region of positive charge density. And the chlorine is red, a region of negative charge density. So we can see that here. This is what we kind of sum up, as far as mapping out the electron cloud goes. To a map like this. Right, delta En 0.9 is polar. Okay, the most polar would be the ionic. And the most ionic we could have is taking the least electronegative. So let's take a look at the electronegativities. We're going to be using Pauling's electronegativities. And we don't want this much precision. Really, if we're going to start using that much precision, we probably should factor in the bonding and everything else. But the most electronegative is fluorine. The least electronegative would be cesium, 0.7. And so the most ionic we could have, the biggest delta En we can have is 4 minus 0.7, which would be 3.3. 3.3 would be the most ionic. And that would be the biggest electronegativity difference between the two elements. What we're going to do is we're not going to use cesium, we're going to use sodium. Sodium chloride should still be ionic. We know that sodium has 1 electron, chlorine has 7 electrons, valence electrons. Chlorine wants that. But we have to take a look at the electronegativities. Sodium has electronegativity of 0.9, chlorine has electronegativity of 3.0. And so that's going to give us a delta En of 2.1. A delta En of 2.1 is in what region? Ionic. And so we expect an ionic. So sodium is going to put up a fight, but it's too weak. And what's going to happen is it's going to lose the electron. And so when we draw Lewis structures for ionic compounds, we don't show a line representing a bond like I did up there. When we draw the Lewis structure for an ionic compound like this, sodium is going to lose the electron. So sodium loses the electron, and so it has no valence electrons. And chlorine's going to take that electron because it's lopsided tug of war here. And so chlorine takes the electron. And so this is showing an ionic bond here. The ionic bond is just so there's a difference in visualizing the bond. What holds the two atoms together? What holds the two atoms together in a covalent bond is the concentration of electron cloud in the internuclear region. which is going to hold the nuclei together because there's negative charge density here. Two nuclei are going to be attracted to the cloud. What holds the atoms together in an ion bond are oppositely charged ions. We have sodium ion and chlorine ion. So what was the strongest covalent bond? You recall what the strongest covalent bond is on the chart? Yeah, nitrogen-nitrogen triple bond. And that costs how much energy to break? 1,000 kilojoules. Do you think light is going to break it? No. No, in fact, this room is filled with 80% nitrogen by mole, by volume, by pressure, but not by mass. So it's filled with, but that 80% nitrogen doesn't do anything. It's what we call a pseudo-inert gas. It's very unreactive. People have been trying to react the nitrogen in air, but it's not easy. Mm-hmm. Difference between sigma bonds and pi bonds? Yeah, I'm going to when I get to. I'll draw a pi bond out pretty soon. No, I haven't explained it yet. So I'll talk about pi bonds in a minute. So the nitrogen that we breathe doesn't do anything. It's unreactive. It's unreactive because that triple bond's so hard to break. Certain things can break it, like there are certain legumes that have enzymes which facilitate the breaking of the nitrogen-nitrogen triple bond. So for some plants, nitrogen is like food. For us, it's not like food. For us, it's fairly inert. Or you can get nitrogen to react with oxygen if you do it under extreme conditions. What are the extreme conditions? Well, air becomes a reactant, an oxidizer, at least the nitrogen. Is it? No. Well, a reducer in this case. At extreme temperature and pressure. And you can get those extreme temperatures and pressures in cars, automobiles, car engines, especially diesel engines, have a problem with nitrogen reacting. And so it's not totally inert. And therefore, when you go for a smog check, they check how much oxides of nitrogen are being produced in your engine. Let's say, but how strong is this bond? Now, the bond energy is tricky here. The reason it's tricky is not because it's not one bond. For example, gold, each gold atom is not bonded to one other gold atom. Do you know how many other gold atoms each gold atom is bonded to? 12. It turns out that sodium isn't bonded to just one chloride. Do you know how many chlorides sodium is bonded to? 6. Turns out it's 6. Four in the plane, one above, one below. Do you know how many sodium's chloride is bonded to? Also 6. Four in the plane, one above, one below. And then what we have to do is we have to look at next nearest neighbor. So if we look at this chloride at the top here, there's going to be attraction to this sodium, but there's going to be a repulsion to this chloride. But then there's going to be another attraction to this sodium. And so what we have is nearest neighbor, then we have next nearest neighbor, and then next nearest neighbor, and so on. The effect of those drops off according to Coulomb's law of the square of the distance. And so the effect of those drops off rapidly. But nonetheless, what we have is, we shouldn't call it bond energy. We call it lattice energy. Because we don't have just one bond, we have a lattice of bonds. Now, lattice energies are very strong, usually. You know, most salts, are they easy to melt or hard to melt? They're hard to melt. Have you ever tried melting table salt? I have, but I wasn't successful. There are some lower melting salts, but they aren't as common. But they're out there. And so lattice energies are very strong typically, on the order of hundreds to thousands of kilojoules per mole. So that nitrogen-nitrogen triple bond was 1,000 kilojoules per mole, but there are some lattice energies that go up to like 3,000 plus kilojoules per mole. 3,000 plus kilojoules per mole. It's a lot of energy that would be required to break apart the lattice or melt it. So there are different degrees. And so what we have is we have the just these qualitative things, non-polar, polar, ionic. But also we could be more quantitative. That is, we could just list how polar it is by stating what the percent ionic character is, or how non-polar it is by stating what the percent covalent character is. That type of stuff. Eventually, what we want to do is we want to have some kind of details as far as the bonds, and then the orbitals. When you look at the orbitals collectively as a whole, and then map out the electron cloud, we come up with this. So we can look at individual bonds here. We can look at the whole collective electron cloud together. Here are some electrostatic potential maps. These are using these meshes. The meshes are kind of nice because it lets you see the bonds a little easier in the atoms rather than surfaces, solid surfaces. Okay. This is PABA, which stands for para-amino benzoic acid. And this is sulfanilamide. You see they kind of have similar structures. You know, when we look at the electron cloud as a whole, they're quite similar. Where do you see a difference? Yeah, on the bottom part. It looks like on the bottom left. You know, this blue region is electron deficiency, so this is more positive. The red region is electron excess, more negative. And so we can see this. Papa and sulfanilamide. These two molecules are important here. This is Illustrated Glossary of Organic Chemistry from UCLA Chemistry. And so I don't think did I show the video on sulfanilamide? No? Okay, I'm going to show you a video on sulfanilamide and para-amino benzoic acid. So let's start. We don't pause the video, so I don't get hit with copyright. Although this video is old. This video is really old, but so I don't think there's any problem with this. So, how would you draw the Lewis structure for sodium carbonate? Well, we know the Lewis structure for sodium ions. Sodium ions have no valence electrons, and they'll have a net charge of +1. And then carbonate, what's the Lewis structure for carbonate? Carbonate is trigonal, it's planar. Polyatomic anion, like this. It's going to have a negative formal charge on this oxygen, a negative formal charge on this oxygen, and a net 2- charge when we add up the two formal charges. Between the sodium ions and the carbonate, we have an ionic bond. Ionic bond is not shown. And again, we don't just have one bond, we have a lattice of bonds extending out in 3 dimensions. But within the carbonate, what is the bonding inside there? Within the carbonate, we're going to have, what's the hybridization on carbon? sp2. So we're going to have bonds here. And so let's take a look at the bonds here. But before we do that, this is just one of the resonance forms for carbonate. What are the other 2 resonance forms? What they look like? Do you guys remember resonance forms? Resonance forms, what's the difference between the resonance forms? The difference between the resonance forms is the position of what? The position of the double bond. And so I drew the double bond up here at the top, but I could have drawn it down here on the right or down here on the left. And so the 3 resonance forms would be one that shows the double bond on the top, the second one could show it on the right, and the third one on the left, or whatever combination.
So I know there's resonance forms where it's, it's not actually a resonance form, it's just you rotated it, but it's actually the same. Why is that even a resonance form? Because can I just say that's the exact same thing, I just turned it?
It is the exact same thing in terms of energy, but it's not the exact same thing in terms of where the electron cloud is positioned. That is, when we do resonance forms, we can't turn it. We have to pin the atoms in position. And so if I call this oxygen A, B, C, then there's going to be a difference in where the electron density is. This one's showing the electron density between oxygen A and C. I mean A and carbon. But these ones would show different cloud distribution. And so what I'm going to have here is I'm going to have more concentrated, because rather than having 2 electrons worth of cloud, I'm going to have 4 electrons. And so I'm going to have much more cloud density here due to the double bond. In fact, let's take a look at the double bond here. The double bonds are going to be stronger. How much stronger is a double bond compared to a single bond, roughly? And so let's take a look at the bond energies again. So if we look at a carbon-carbon single bond, 347, the carbon-carbon double bond is 611, so it's about 2 times stronger. The triple bond would be about less than 3 times stronger, but we'll just say 3. Just take the number raw. And so this double bond is going to be about twice as strong. When we look at the double bond, I'm going to draw this in profile here. And so the double bond is going to consist of an sp2 hybridized carbon. And what's the hybridization on this oxygen here? sp2. And I'm going to look at this by a side view. We'll have a pair there. In terms of a side view, I'm going to put the p orbitals in the plane of the page. And that means the other sp2 orbitals stick out. Well, I'm going to have one sp2 sticking out. I'm going to have a lone pair in there. And another sp2 sticking in. This will have a lone pair here. And then I'll have an sp2 again sticking out. Another one sticking in. These sp2s down here are going to be bonded to the oxygens right here. And so we have a sp2 sigma bond because the overlap is within the internuclear axis. So the internuclear axis is just a line drawn through the two nuclei. But when we look at the p orbitals overlap outside to the right and outside to the left of the internuclear axis. They don't actually overlap on the internuclear axis because we have a node there. And so this is called a p-p pi bond. P-p pi. Pi bond is when you have the overlap outside. Now they don't look like they overlap, but you know the orbitals are actually infinitely large. We just combine them to their 95% probability boundaries, but the electron cloud is going to be on both sides of the internuclear axis. So the electron clouds on both sides. Now, the stronger bond will be the sp2 sigma, because the nuclei are positively charged and they're going to be directed towards each other with this overlap here in this region. The sp2 sigma is stronger than the pp pi because the pp pi, the nuclei are going to be attracted to the region to the right and to the left. Whereas in the sigma, it's straight on to this carbon. So this is sigma. This is going to be attracted to this cloud and this cloud over here. And we have that. Now, if we draw the resonance forms for carbonate, you could say that they're exactly the same thing, but what we have to do is we have to look at how the electron cloud can be delocalized in the structure. And so let's draw the resonance forms for carbonate here. So one resonance form is like this. Sometimes we just draw the formal charge and not the whole net charge. The other resonance form is like this. And the third resonance form would be like this, in no particular order. And while it's true, these are all related by what we call a threefold rotation axis. If I rotate this 120 degrees, then I get the other version here. So if I take this one, rotate it counterclockwise, 120, it overlaps with this one. The same thing, take this one, rotate it 120, and then rotate it 120 again. We're back to the original starting point. So it takes 3 rotations to come back where we are. So it's a threefold rotation axis. And so they look exactly the same because they are exactly the same. They're exactly the same, but they aren't exactly the same. They're exactly the same structure. They're going to have the exact same energies. However, they aren't the same because what we're seeing is how the electron cloud can be moved around in the particular structure. So for example, here, what I can do is I can take this lone pair, make a bonding pair, and kick this bonding pair out, and then I generate this. Or I can take this lone pair, make it a bonding pair, and kick these out to make it a lone pair, and I generate this structure here. Or then I can just go back to this structure here. And so what it shows is how the electron cloud, or how the electrons can be redistributed in the molecule. But more than that, it turns out none of these are correct. You know, double bond is shorter and stronger than a single bond. We'll talk about bond lengths later. Bond lengths come in chapter 11. But double bonds are shorter and stronger. Why? They're shorter because there's going to be a stronger attraction here between the nuclei. There's more electron cloud density there. Triple bonds are even stronger. You know, the strongest bond was a triple bond up there, the nitrogen-nitrogen triple bond. But it turns out when you analyze carbonate, all the bonds are of equal length. And what each of these drawings shows is localized electrons. So if I just fix one of these, what I'm saying is that the electron cloud is localized at the top. And that's localized. Or pick the next one. Electron cloud is localized on the left, electron cloud is localized on the right. Well, the reality is that the electron cloud, like water or fog, just spreads out. If there's capability of redistributing it, then it's going to redistribute to even itself out. And so when we think about this, I'd like to draw a bathtub that's Y-shaped, with this inverted Y. And so if this is a bathtub, and you put 2 feet of water here, that would represent the double bond. And then you put 1 foot of water here, and 1 foot of water here. Is that a sustainable situation? No, water is going to seek its own level. And so you can't put 2 feet unless it's localized. That is, if you put a wall here and the electrons can't move, then that double bond is what we call localized. It can't move. An example of a localized double bond would be something like this. This would be a localized double bond because we can't really rearrange this. I suppose you can try to double bond chlorine, but chlorine doesn't want a double bond because it'll get a positive formal charge. Chlorine doesn't like to be positive, like fluorine. And so here, this is localized. We aren't going to draw resonant forms for this because all of those are going to be much more unstable. So for example, if I tried to draw a double bond with chlorine, that's going to screw up all the formal charges. And so this does not look as stable as this. This looks quite a bit more stable because there are no formal charges. Unstable. Whereas if I tried to rearrange the electron cloud here, that is, there's no problem because they're all the same in terms of energy. But what that means is that the electrons can move. There's no wall. Over here, there's a wall blocking it. And so there's no problem maintaining 2 feet, double the density here, and half the density here and here. Over here, there's a problem. If we have double the density here and half the density here and here, what's going to happen is everything's going to spread out and become even. And so this is not sustainable. What's sustainable is, this is called localization. What's sustainable is delocalization. They're going to try to want to delocalize if it's possible. In the case of carbonate, it's possible. In the case of carbonyl chloride, it's not possible. And so for carbonate, we have no problem because the electron cloud can distribute itself evenly across here. And so what we end up with is not 2 feet and 1 feet, we end up with 1 1/3 foot of water. And so the real picture of this is not any one of these. The real picture of carbonate is what we call a hybrid structure. A hybrid structure has 3 equivalent bonds. Each bond is a 1 1/3 bond. And a formal charge here is not -1, -1, 0. The formal charge here is -2 divided by 3 atoms. It's -2/3. Would be the cloud density on each of those. And we have 3 oxygens at -2/3 each, gives us a -2 net charge. So this is the hybrid structure. The more you can delocalize, the more stable the structure is. And so in terms of resonance, the more resonance forms we can draw, the more stable we expect the charge to be or the species to be. And so it's just a simple matter of counting how many resonance forms. In this case, we have 3. In other cases, we have 2. So 3 resonance forms is going to be more delocalized, hence more stable. However, when we're doing our analysis with valence bond theory and overlap of atomic orbitals, we pick one of these. We don't do the hybrid. We just pick one of these and analyze it. And so I just picked that one with a double bond coming up, and this is what we see with the double bond. And we see that extra pair of electrons almost double the bond energy, even though it was not. If it were a sigma, so let's say we have 4 electrons sigma, then yeah, maybe it would double. It's less than double because the pi's aren't as strong. Oops, I'm out of time, sorry. Okay, we'll stop here. Look at it next time.